Hey guys, welcome to section 6.2, factoring special cases. We did an introduction to factoring in 6.1. We're just going to expand on that a little bit. We'll talk about special cases in a moment, but first, let's take a look at this product. Remember, factoring is the reverse of multiplication. So just like last time, we're going to start with multiplication and see how we can reverse it. Let's look at the product, x minus 3 times x plus 3. These are two little binomial expressions. When we're multiplying two or more expressions that have two or more terms, we use the distributive property. When they're both binomials, we can do the FOIL. We can use a FOIL acronym, first, outers, inners, last. In other words, we're going to take this x, multiply it by both terms in the second parenthesis, so the product of the first would be x squared. And then the product of the outers would be the x times the plus 3x. And then we're going to multiply this minus 3 times each of the terms in the set of second parentheses. So we did first outers, and then the inners would be minus 3x. And then the last would be minus 3 times positive 3, which is going to be minus 9. Now notice in this situation, the inner and the outer terms cancel. They're the same term but opposite in sign. So this just reduces down to x squared minus 9. Now take a look at this result. What I want you to notice is that this is the x times the x from right here. And this 9 comes from multiplying the last. And then because these values are the same and the signs are switched on the inside, the inners and the outers cancel. So this would be the negative 3 times the positive 3 from here and here. All right, let's try x minus 4, x plus 4. Well, the product of the first x squared, product of the outers, or the x with the second term in the second set of parentheses, plus 4x's. Now we're going to distribute the negative 4 to each term. We're going to do the inners, minus 4x, and then minus 4 times plus 4 is minus 16. These guys are going to go away, and my result is x squared minus 16. Again, take note, this x squared term came from multiplying this x and this x, and this minus 16 came from multiplying that minus 4 and that positive 4. This isn't a coincidence. What we'd like to do is be able to work backwards. If I gave you the expression x squared minus 16, could you break it down into the the product of the two binomial expressions, x minus 4 and x plus 4? Likewise, if I give you x squared minus 9, could you notice that that could be broken down into x plus 3, x minus 3? When we're given an expression like this, it's called the difference of squares, because we have a difference between two terms. This is x squared, and this is a nice whole number, 4 squared. So this is x squared minus 4 squared. And up here we have x squared minus 3 squared. So I'll just do a little note, x squared minus 3 squared. And this is x squared minus 4 squared. Whenever we have an expression that can be written as the difference of two squares, it always factors. Tricky part is recognizing the difference of squares, and that just comes with lots of practice. So the difference of squares always factors. We have a little template. So depending on how you want to write it, the difference of squares, let's suppose I had something squared minus something else squared. This always factors into two little binomial expressions. What's going to go first in the set of parentheses is what was squaring here, but without the power of 2. And what's going to go second is what's being squared second, which is the b. And then we're going to do opposite signs. You could do plus minus, it doesn't matter. I like to do minus plus, right? And whatever you're squaring, triangle squared minus square squared, something squared minus something else squared, always factors. It's going to be whatever's first is going to go first here. Whatever's being squared second is going to go second in the parentheses. It's going to be minus plus, or plus minus. Again, doesn't matter. Multiplication, we can switch the order in which we multiply. You want to do enough of these that you can recognize the patterns and trust the factoring process. I call this my corny cloud with stars. If it's a corny cloud with stars, if you see that, it's important and you really should focus and memorize that. All right, let's look at m squared minus 81. If we look at it, just the two terms, m squared and 81, m squared and 81 have no greatest common factor other than 1. There's no m here, and the coefficient here is 1. So we can't pull out a greatest common factor. We have to remember that's the first thing we always look for. But we can write this. We can ask ourselves, it's a difference. I see a square, so ask yourself, can I write this as something squared minus something else squared? So what would I put in the parentheses such that when I square it, I get m squared? Well, hopefully you just saw the obvious and it's just m. M squared is m squared. So what can I square? Is there something I can square nicely and get 81? Well, hopefully you recognized or remembered that 9 squared is 81. So we can write m squared minus 81 as m squared minus 9 squared. Now this fits this template. This is the difference of squares. So this definitely factors. It's going to be m here, 9 here, 9 here, plus minus. Right. Now the purpose of factoring is to break down the powers on the polynomial. Here we have a second degree expression, a second degree polynomial, and we broke it down into the product of two little linear expressions. The power on both of these m's is 1. This mathematically is much easier to work with. So we're going to use factoring as a tool to help us solve harder problems down the line. So you want to be really good at factoring. Right, so let's check. M minus 9 times m plus 9 is, well, m times m squared, the outers, plus 9m's. Now notice because of the sign change in the middle, the inners are going to give me minus 9m, and then minus 9 and plus 9 is minus 81. These guys, the inners and the outers, are going to cancel. We have the m squared, and always keep the sign to the left of the term. It's going to be m squared minus 81. Therefore, m squared minus 81 completely factored is m minus 9 times m plus 9. Final answer. All right, let's try another one. All right, let's factor p squared q to the 4th minus 100. All right, well, this one's a little bit of a step up in difficulty. What I do notice here is that this is 10 squared, and I see a squared here, but we have to be able to write this as something squared minus something squared. Right, so hopefully you see we can put a 10 inside these parentheses because 10 squared would give me 100. Now, can I put anything in here such that if I square it, I get p squared and q squared? Well, notice if I put p here, p squared will be q, p squared will be the p squared term, but I can put some q's in here. What would be the power on the q such that if I squared it, I got q to the 4th? Well, hopefully you said q squared. Notice p times q squared times p times q squared is going to be p times q squared, which is p squared, and q squared plus q squared, we add the exponents, is q to the 4th. So remember, when you have a power to a power, you multiply the power. So there's a 1 there that we don't see, so that's p squared and q to the 4th. So my goal was to write this as something squared minus something squared, and we did. So this is an expression that can be written as the difference of two terms squared. So now we know we can factor it. So what I suggest to students is as soon as you write it as something squared minus something else squared, cover up those 2's. That's going to be the first term, p q squared minus 10. And then the second term, I just write the same thing again, but then you change the minus to plus. And to do, check. You can always check factoring by multiplying. So p squared q to the fourth minus 100 can be written as the difference of squares, pq squared, whole quantity squared, minus 10 squared, which in turn can be written as the factors pq squared minus 10, pq squared plus 10. So what's important is to keep in mind your perfect square numbers. So if we go back to these couple problems here, 81 is a perfect squared number because it can be written as 9 times 9. 9 is a perfect squared number because it's 3 times 3. 16 is a perfect squared number. So we want to start recognizing or be able to recognize at least some of the lower perfect squared numbers. So for example, 1 squared is 1. 2 squared would be 4. 3 squared is 9. 4 squared is 16. 5 squared is 25. 6 squared is 36. 7 squared, look for 49. These are the numbers you want to look at, and keep in mind that these can be written as other numbers to the power 2. 8 squared, 64. 9 squared, 81. 10 squared, 100. 11 squared, 121. 12 squared, 144. And I could go on forever. 13 squared, 169. 14 squared, 196. The list goes on forever. Another couple of reminders. Remember your power properties. So a product, products of x to a power, x to another power. We add the powers. This would be m plus n. So for example, if we had x cubed times x squared, well, keep in mind that just means x times x times x. That's x cubed times x times x. That's x squared. And how many x's do we have? X to the fifth. Would have been a lot easier just to add the powers, especially if those were bigger numbers. So when you have a base to a power, the same base to a power, you can combine them by adding the powers. If we have a power to a power, we multiply m times n. So for example, if we had x cubed squared, well, if I use this template, it's going to be x to the power 3 times 2, which would be 6, but let's just write it out to see that. This means x times x times x, that's the x cubed in the parentheses, all to the power 2. The x squared means x times x times x times x times x times x, which is x to the 6th. So we want to skip these steps, trust the templates. X cubed times x squared, we would add the powers. X power to power, we multiply the powers. So just some things to remember. All right, let's go back to our difference of squares. Do a couple more problems. All right, let's look at 1 minus 9b squared. I see a squared, I see a minus, so I ask myself, can I write this as the difference of something squared minus something squared? Now, 1 is one of the trickiest numbers because its simplicity can be complicating. I know that sounds silly, but it's true. Don't forget that 1 is itself squared. So 1 can actually be written as 1 squared. Then what can I put in the parentheses here such that if I squared it, I multiplied it by itself, I got 9b squared. Well, hopefully you see that if we square the 3, we get the 9. And if we put b in here and we square it, we get b squared. So take time to check. 1 squared is 1 minus, well, 3b times 3b would be 9b squared. So we can write this expression as the difference of squares, and the difference of squares always factors. Cover the powers. The first term is going to be 1 minus 3b. And then I just write 1 minus 3b again, and then change the minus to a plus. And you can check. Do. First, inners, outers, last, and you'll see that you'll get what we started with. So again, our goal is to do a power reducing here. So we started with a second degree expression, and we wrote it as the product of 2 first degree expressions. All right, factor 10z squared minus 40. Well, I see a z squared, but 40 is not a perfect squared number. There's no number we can multiply it by itself to get 40. So before we conclude, we can't factor this. Don't forget the greatest common factor. So notice 10z squared and 40 share a factor of 10. I can pull the 10 out, and if I pull 10 out, we're left with z squared in the first term minus, well, I could have a 4 here. So 10z squared minus 40 is equal to 10 times z squared minus 40. Now, when you're asked to factor, it's understood that you will completely factor. So what does that mean? We have to look in the parentheses and say, can I factor what's inside the parentheses further? Well, if we forget this 10 for a moment and look at z squared minus 4, if you notice, this is just z squared minus 2 squared. So what's inside the parentheses is a difference of squares. So we can break z squared minus 4 down further into z minus 2, z plus 2. So we have to factor completely, always. Just like when we were asked to factor 12, and if we did 6 times 2, that's not completely factored. We want to break the 6 down further. We want everything to be prime. What's left has to just be, the factors can only be 1 in itself. So the only factors of 3 are 1 in itself. The only factors of these 2's are 1 in itself, and together multiplied, that gives me 10. So the only z squared minus 4 is not completely factored. We did part of the factoring. We pulled out the greatest common factor first, and then we did difference of squares, which remained inside the parentheses. Now you have to be careful because this 10 has got to come along down for the ride. It doesn't go away. We have to make sure we put it back out front. So therefore, my final answer, 10z squared minus 40, completely factored, is 10 times z minus 2 times z plus 2. Okay. All right, let's look at this guy, 75m to the 6th minus 48. All right, well, this may not be super completely obvious, but 75m to the 6th, we can write m to the 6th as something squared if you think really cleverly here. 75 and 48 aren't perfect square numbers, but don't forget to pull out a greatest common factor. Does 75 and 48 have a common factor? Well, you start picking away. Let me see, 75 is 1 and 75. It's 5 and 15, maybe. Doesn't 5 or 15 doesn't go into here. About 3 and 25. Does 3 go into 48? As a matter of fact, it does. So we can pull out the greatest common factor first. Don't forget to do this. This is one place, students, don't forget the last section. We pull the 3 out, and we're left with 25m to the 6th minus, well, we pull the 3 out here, we're at 16. What do you notice? 25 and 16 are perfect square numbers. Right, so now, before we conclude we're done, make sure we're just going to ignore this 3. It's going to go along for the ride. We're going to ask ourselves, can I write this as something squared minus that something squared? Well, 4 clearly gives me 16. 5 squared gives me 25, but what would the power on m have to be such that when I squared it, I got 6? We would have a power to a power, so I need a number here such that the product of this number and 2 is 6. And the answer is going to be 3. So 25m to the 6th minus 16 can be written as 5m cubed squared minus 4 squared. So this is the difference of squares. And we get super excited when we see difference of squares because we know the difference of squares factors. And you just cover the powers, and it's going to be 5m cubed minus 4. And then this is going to be 5m cubed, but we're going to change it to plus. And then don't forget this guy. The 3 has got to come down. We can't forget that. If you forget that and put in Alex, it's going to mark it wrong. So therefore, 75m to the 6th minus 48 can be broken down into 3 times 5m cubed minus 4 times 5m cubed plus 4. Kind of fun, huh? All right. Let's try one more of these squares problems. All right, factor x squared plus 16. Well, notice this is x squared plus 4 squared. but not a difference. This is the sum of squares. So you can sit here and you can take x squared plus 4 squared, and you can try breaking it down. I'm going to let you try if you want to sit here for the next however many days and trying to factor this. I'm going to tell you right now, this will not factor. There's nothing you can put in these parentheses such that when you redistribute, you get x squared plus 16. Okay. If you do find something, send it to me and I will give you an A for the entire semester. Fact: the sum of squares does not factor. Unless there is a GCF. You can only factor a greatest common factor out of the sum of squares if one exists. Here, no GCF, 1x squared and 16. There's nothing we can pull out. There's no greatest common factor other than 1. So no GCF here. Therefore, x squared plus 16 does not factor. That is, it's prime. When we have an expression that does not factor, we call it prime. The sum of squares, unless there's a greatest common factor, does not factor. So look at this guy. Keeping in mind that you always want to pull out the GCF first. So don't forget the GCF. That's the very first thing we learned in factoring. We pull a 4 out, we get x squared plus 9. Sum of squares doesn't factor further. Right? And I'm not saying this expression doesn't factor at all, because we did pull the 4 out. So we did a little bit of factoring, but what's left in the parentheses does not factor. So therefore, 4x squared plus 36 factors only by pulling out the greatest common factor. And that would be our final answer. So the difference of squares always factors. So if I have z squared minus w squared, something squared minus something squared, it's always going to factor. What's going to go first in both sets of parentheses is what's first in the expression, z. What's going to go second in both sets of parentheses, it's what's second in the expression. One's going to have a minus and one is going to have a plus. You can switch it. You can do plus and minus as long as one term has a plus and one term has a minus. I do it this way for a reason. And that reason's coming up next. And that's the difference of cubes. If you can write an expression as something cubed minus something cubed, it always also factors. I'm going to give you the template. Something cubed minus something else cubed is going to factor. The first factor is, well, you take what you're cubing, cover up the powers. There's going to be what's being cubed minus what's being cubed second. And then, right, bear with me. So once you have these established, what's going to go first in the next set of parentheses is whatever you have here times itself. So this times this. So A times A. What's going to go in the middle is this times this. A times B. And what's going to go on the end is this times this. Right? Now we have to be careful with the signs. Whatever's in the first set of parentheses, it's the same sign that we started with. And then both of these, regardless of what's here, is going to be plus and plus. So in other words, it's going to be a minus b times a squared plus the first term times the second term plus the second term squared. Same sign that we started with. We switch the sign, and then the last one is positive. Difference of cubes always factors, always. Just like the difference of squares. And this is the template we can use. Okay, and mathematicians developed this template through noticing patterns. Math is a lot about patterns. So x cubed minus 27. Well, notice x cubed minus 27 is something cubed minus 3 cubed is a perfect cube number. 3 times 3 times 3 is 27. So I can write this expression as x cubed minus 3 cubed. And if I can write it as the difference of cubes, it will factor. So what's going to go first in the parentheses? Just cover the powers, and it's going to be x minus 3. So x minus 3. And then what's going to go in the second set of parentheses? Well, I ignore what's going on up here. I forget what I even started with. What's going to go here is whatever's here, I'm going to multiply that times itself. So x times x, which is x squared. What's going to go in the middle is the x and the 3. Multiplied together, 3x. And what's going to go on the end is that times that, which is 9. And here's where you just have to remember, if we start with subtraction, the first parenthesis is subtraction, then it's addition and addition. So here we broke x cubed minus 27, a third degree polynomial expression, into the product of a first degree or linear and a second degree. So our goal of factoring is to break down powers and make them into products of smaller expressions. So let's just double check. And this is one that you want to get good at the template and trust it and not have to check it anymore. So this time we can't FOIL because we have a trinomial, a 3-term expression over here. So we're going to take x and multiply by each of these 3 pieces. So x times x squared was going to be x cubed. X times the 3x would be plus 3x squared. And then x times plus 9 is going to be plus 9x. Then minus 3 times x squared, minus 3x squared. Minus 3 times plus 3x, minus 9x. And then minus 3 times positive 9, minus 27. Notice everything in the middle cancels out. And all that's left is x cubed minus 27, is what we started with. So this would be my final answer. X cubed minus 27 factored completely is x minus 3 times x squared plus 3x plus 9. So now here, this one's a little bit trickier because we have to get in the habit of looking for perfect cube numbers. You might not have recognized 27 as a perfect cube or as 3 times 3 times 3. So perfect cube numbers that through the process of doing lots of examples, you're going to start remembering. 1 is a perfect cube number. This is just 1 cubed. 2 cubed is 8. So 8 is a perfect cube number because we can write it as 2 times 2 times 2. 27 is a perfect cube number. Now these numbers get bigger much quicker. 3 cubed is 27. 4 cubed, we're already at 64. So 64 is 4 cubed. 5 cubed, we're at 125. 6 cubed, we're at 216. 7 cubed, we're at 343. I can keep going, but I'm just going to put those for now, but it goes on indefinitely. I'm going to do this. Factor 343b cubed minus 8a cubed. It's a difference. I see powers of 3. So, maybe this is the difference of cubes. Can I write this as something cubed minus something cubed? Well, 343, I just pointed out that that happens to be 7 cubed, and you just want to get good at these. You just want to start recognizing them. So I can write this as 7b inside of here because 7b times 7b times 7b is going to be 343b cubed. 8a cubed, well, 2 times 2 times 2 is 8. 8 is a perfect cube number. It's 2 cubed. And then I can put the a here. So we can write 343b cubed minus 8a cubed as the difference of cubes, 7b whole quantity cubed minus 2a whole quantity cubed. Now if we use this template, it says the first term in the factor, just take the powers off, it's 7b minus 2a. Okay, and now the second one's a little more complicated, but if you start trying to follow this process, once you have the 7b and the 2a, what goes first here is just this times itself. So it's that times that. So 7b times 7b. I'm going to do that, 7b times 7b. You can just write 49b squared if you're comfortable. What goes in the middle is going to be the 7b times the 2a. So 7b times 2a. And then what's going to go at the end is 2a times 2a. Now I know you might want to like fuss around with the signs, but trust the process. It starts, whatever we started with, that's what's going to be first in the first set of parentheses. And then we're going to switch the sign to positive, and we're going to leave the last sign positive. So let's just clean this up. 7b minus 2a can be written as, 343b squared minus 8a cubed can be written as 7b minus 2a times 7b, 49b squared, 7b times 2a, 14ab. You can write ba, but we tend to write the variables in alphabetical order. And then 2a times 2a is 4a squared. And we are done. All right, kind of cool. Check it if you want, or you can just start trusting the process. All right, so difference of squares, always factors. Difference of cubes, always factors. Sum of squares, unless it has a greatest common factor, does not factor. But interestingly, the sum of cubes always factors. Sum of cubes always factors. If we have something, if we can write as an expression as something cubed plus something cubed, it's always going to factor. The first factor is, we'll hide the powers. It's just each term without the cube power. What goes next in the second set of parentheses is whatever's here times itself. So a times a, which is a squared. What's going to go in the middle is a times b. What's going to go on the end is b times b. So this looks an awful lot like the difference of cubes template right here. So here's the difference of cubes template. This is the sum of cubes. Notice in both of them, whatever sign we start with, that's the sign in the first set of parentheses. Now here's where it changes up a little bit also. If it's an addition, we have addition in the first set of parentheses, we switch the sign to minus, and then we end with positive. The same sign we start with, we switch the sign, end with positive. Same, opposite, positive. So anytime you recognize something as the sum of cubes, it's going to factor, and that's the template we can use. So don't forget, 1 is a perfect cube number. It's 1 times 1 times 1. We see a cubed, and we recognize 27 as 3 cubed. So this is equivalent to 1 cubed plus 3m cubed, because 3m times 3m times 3m is 27m cubed. We say, oh wow, that's the sum of cubes. This is definitely going to factor. So my first factor in the sum of cubes, ignore the powers, and what's remaining is the first factor, 1 plus 3m. All right. Now what goes first in the second set of parentheses is what's first in the first set multiplied by itself, so 1 times 1. What goes in the middle is the first times the second, 1 times 3m. And what goes at the end is 3m times 3m. Now the signs, we started with a positive. Same sign we start with. We're going to switch to the opposite sign and always end with a positive. And now we just clean this up. 1 plus 3m times 1 minus 3m plus 9m squared. So 1 plus 27m cubed can be broken down into 1 plus 3m times 1 minus 3m plus 9m squared. So let's do one more that's a little bit trickier. I see a sum, I see a cube, keeping in mind that these powers are both multiples of 3. Also, 64 is a perfect cube number. Careful, 64 is both a perfect square and a perfect cube number. 64 is 8 squared, so we can use it in the difference of squares. We can also use it in the sum and difference of cubes because it's 4 cubed. So we ask ourselves, to sum, can we write it as something cubed plus something cubed? Well, x, that's easy because it already has the power of 3. So if we brought that in, we'd get our x cubed. So what power would we need to put on y such that when we cubed it, we get 6? Remember, it'd be a power-to-power relationship. So the power we would need on y would be 2. We bring the power in, would get x cubed and y to the 6th. 64 is 4 cubed, so we can put a 4 inside the parentheses. And then z to the power 4, all cubed, would give me z to the 12th. So we can write x cubed y to the 6th plus 64z to the 12th as x y squared cubed plus 4z to the 4th all cubed. As soon as we can write it as the sum of cubes, we can use this template up here. For difference of squares, difference of cubes, and sum of cubes, your first term, always just hide the powers. It's going to be x y squared plus 4z to the 4th. Now the second one can be complicated, or you don't have to make it complicated. What goes first in the second set of parentheses is just the first term here times itself. xy squared, xy squared. What goes in the middle is the product of these two together. So xy squared times 4z to the 4th. Oh no, I'm going to run out of room. And then what goes last is 4z to the 4th, 4z to the 4th. Sorry, ran out of room. Right? Now where you have to be careful is the signs that you used. If we're doing the sum of squares, we keep the sign the same in the first set of parentheses. We switch it to the opposite sign, and we always end with positive. So I'm going to clean this up. xy squared plus 4z to the 4th. xy squared, xy squared. It's going to be x squared y to the 4th. We add the powers. Minus xy squared 4z to the 4th. We typically put the constant coefficient out front and then leave the letters in alphabetical order. xy squared z to the 4th. And then 4z to the 4th. 4z to the 4th is 16z to the 8th. And that would be your answer. All right, so just to sum it up, so you have it all on one page, the difference of squares, m squared minus q squared, always factors, take off the powers, m minus q, m plus q, difference of cubes, l cubed minus, and I'm running out of letters, p cubed is first factor, L minus P. What's going to go here is L times L, L squared. What's going to go in the middle is L times P. And what's going to go at the end is P times P. Same sign, switch it to the opposite sign. Always end with a positive in the difference in sum of cubes. W cubed plus C cubed is W plus C. And it's that times that. W squared is first. What goes in the middle is W times C. And what goes on the end is C squared. Same sign, opposite sign, positive. All right, have fun with factoring. See ya.